All right. Thank you, Sean. I'm Soil Sajjadi. I'm located in Charlotte, North Carolina, working for Arcadis, but most of my work is national and international using different software platforms. I'm also active at Transportation Research Board. I'm a member of the Transportation Research Board Highway Capacity and Quality of Service, which is this duty is really publishing the HCM, and I am the Connected Autonomous Vehicle Group Lead at that committee. It's interesting that we started doing the CAV analysis with Enoch back in 2016, and we published one in 2018, and we had to write, I think, 200 lines of code or something like that, to maybe even more, to mimic the CAV environment. Now it's becoming way more easier with the incorporation of the coexist driver behaviors, which I'm going to talk about, and some of our scenarios are based on that, actually. So this effort, really, the motivation behind this effort was to kind of bridge with our environmental group. You know, Arcadis has a strong environmental and water group, so we wanted to find some new business development opportunities, and vSIM is a very suitable tool to do for the micro simulation tool to calculate emissions. So we wanted to show them that, hey, we have a software that can do emission analysis, and it's relevant. So we go after some project in interdisciplinary projects on the overlap of environmental and transportation engineering. That was the whole motivation. You said it's not a paid project, but it was internally funded project by Arcadis. So I'll give you a little bit of background and then some research objective, show you the project area, the methodology, results, and debrief my presentation with some conclusions. So sustainability and transportation is a hot topic these days, especially for our company. Really is careful about it's a sustainability, and I think it's a good path to go for considering global warming and everything. So we decided to we have decided to do more effort in that regard, because also our company is going into that relation. So let me, this is a multiple choice question. Let's get some vote on what do you think about work zone projects account for how much non-recurring congestion. I think there was a presentation yesterday. They defined a non-recurring, that is something that is not typical. It's something that happens. For example, weather, work zone. How many do you think is 15%? 25, 35, or 45? Okay, yeah, thank you for that. Actually, the correct answer is 25, which is still quite a large number. So we do have a lot of work zone, and one of the reasons that we did work zone, because we show you that emission analysis is really, the sensitivity shows itself in the analysis when there is a congestion. So work zone makes the road more congested, and also the previous study was also based on work zones, so that's why we focus on work zones as well. It was a dissertation of one of my colleagues, George, who is not Texas A&M TTI. He left like 3 months ago. He wanted to pursue research, so he went to TTI. But it was the continuation of his dissertation. What we did, we added the CAV. We infused the CAV model into the dissertation, and almost repeated the analysis with the CAV. But there was some challenges because we were changing. We did it in vSIM 2021. There were some challenges that bringing the old vSIM model to 2021, and I will talk about it when we get to the details. So we wanted to do so. Our environmental agencies are really working closely with Environmental Protection Agency, EPA, and also MOVE's model is something that US uses a lot for EPA. Actually, it's a model for EPA. It's called Motor Vehicle Emission Simulation. So that's a methodology that we had to write a script, a Python script to calculate moves, post-processing the data, and we wanted to get the emissions based on moves model. We define certain market penetration rates as 0, 20, 40, 60, 80, and 100. And we also vary the driver behaviors based on the coexist projects which are embedded in vSIM right now as cautious, normal, and aggressive. And then we also infuse electrical vehicle market share to see the impact. That's also another hot topic these days, electrical vehicles, which we know that they're getting popularity, and some countries like Germany, I think, or Europe, they are estimating that in like 10, 20 years they would not have any more diesel or gas vehicles. So that's also important. And we consider them in our analysis. So let's take a close look at the project area. The area is actually was in New York, New York NY 400, our expressway, Erie County. It was a limited access, limited access free, divided principal area arterial in an urban area. 2 lanes in each direction, and the length was 5 miles. Our work zone scenario was to close 1 lane. We accessed the data from traffic counts, vehicle compositions from New York State DOT, and we calibrated the vSIM model based on a study that was done, I think in North Carolina back in 2016. They calibrated the Whitman 74 and 99 driver behavior models for work zone scenario, and we used the scenario of 2-to-1 lane closure. So we calibrated vSIM based on that study. It was actually NCHRP project 3-107. It was a general guidance for that, and the speed limit was 65 miles per hour on main line and 25 miles per hour on ramps. So this is the a sketch of the study area. So we had some upstream area, then advanced warning area, activity area, and downstream. So that's a clover leaf interchange that you see in the middle. It's an expressway, 2 lanes in each direction. So what we did as methodology, we developed vSIM, we fine-tuned the vSIM, we ran simulation, extracted results. We do some data processing and emission analysis and analysis of results, because we needed to have our own script to calculate moves. We gathered second by second data and then wrote a Python code, and I will show you briefly explain how moves calculates emissions on CO2. There was some challenges, actually. First, we were getting results that was not making sense. Then we went back and debugged everything. We saw that vSIM model is working fine. And then we find the error in the script, so we fixed that. So there were some challenges in that perspective as well. When you're working with the scripts in vSIM, you need to be careful because tracking the error source might get challenging. So we decided we ran our sensitivity analysis. We generated 48 scenarios. One of the varying parameters was demand as low, medium, and high. The CAV market penetration rate 0, 20, 40, 60, 80, and 100%. And CAV driver behavior, cautious, normal, aggressive. Total of 48 scenarios. We ran each of the scenarios 10 times to get the appropriate confidence level. And so it was total of 480 runs, which we divided between ourselves. There was like 5 people working on this, and then ran and generated the results. One thing that I want to share is that I think when we are developing such scenarios, it's better if there's a time and to calibrate, those market penetration rates separately, that's something that we experience a little bit of challenges on 100% market penetration rate, or sometimes on or 80 on high market penetration rates, because it is like when you get 100% CAV, it's going to be far from now. So the model really is doing good job, and you all show the result that it makes sense. But when we get to the high market penetration rates, it becomes very challenging for the model to estimate the behavior. So it's good to, and also when you have these number of scenarios, what we did, we saw some results that was not making sense. We went back to the simulation. We saw, okay, there's a problem here. We need to do change, tweak to make the vehicles move. So that's something. And I should add that we did not consider platooning, because platooning is the function is irrelevant for emission analysis, and we checked also with the headquarters, and then that you cannot do emission analysis by platooning, but it was fine. So we did we proceed with just the CAV driver behavior and lane changing parameters. So a little bit explanation about an emission analysis. I'm not an emission person. This was George really part, but really it moves. What it does, it has something called VSP, VSPs, vehicle specific powers, and then then divides the state of the vehicle at certain second. If I'm not wrong, defines it into a bean, and then from that bean, which I will show, I think I might have the slide for you. From that, so it creates VSP beans, and then from the VSP beans, it says, okay, if the vehicle is at this bean, based on the VSP and based on the character of the vehicle or movement of the vehicle, it's either idling, decelerating, or accelerating, and the VSP it creates a bean. And then the VSP calculation, these AVCs are constant, M is mass still constant, V is vehicle speed, and A is acceleration. So only speed and acceleration, we get it from VSIM. We did the Python code to calculate the VSPs, bin them, and then get the emission results from the simulation, and then it was based on the moves model. The input data, the calendar year was 2015, because we wanted to have apple-to-apple comparison with the base scenario. Region was Buffalo, 23 links. We 23 links in VSIM. We did not include trucks, because the original model also did not include trucks. So we just model everything as a passenger vehicle. Fuel type, gasoline, until we infuse the electrical vehicles. And then some default parameters which moves has, temperature, relative humidity. These are the moves input data, and these are the beans which I explained a little bit. So based on the vehicle state, operating state, and the VSP, which is calculated by that formula that I showed you, which is based on the speed and acceleration and vehicle mode, it puts that vehicle in that certain second into one of these beans, and then from these beans it gets the emission, the CO2 equivalent. These are the beans that was in the previous slides, and then it gets also the energy consumption. And the unit is actually, these numbers are too big for a second. Actually these numbers are for hours, which is 3,600 seconds. So these numbers should be divided if you want to have the equivalent in seconds. So that's how it works, and really why we did that, because we wanted to work with EPA. We were looking for getting contracts from EPA. They work with moves, and that was a whole motivation. Other than that, VSIM has built-in emission analysis, and recently, I think last year, Bosch also introduced the emission module for VSIM. So let's take a look at the results. This is my favorite part of the presentation, because I think we got a very reasonable results at the end. These are the chart on the left. This is the CAV market penetration rate, 0, 20, 40, 60, 80, and 100. And this is energy consumption rate, 4,000 to 14,000 kilojoule per hour. And as you can see, this blue in the middle is a normal driver behavior. Purple is cautious and orange is aggressive. So it makes sense that if you think about us driving, if we drive too slow, or if we drive too aggressive, pushing on acceleration, deceleration, push on the gas pedal, then we create more emissions. But if you drive normal, then the emission that's when the emission is minimized. And as we introduce more CAVs, the emission went down for the normal scenario, but as you can see, we did not get much of the benefit for the cautious or aggressive CAV driver behaviors. And also this chart, there's a point here that I want to highlight also with the safety analysis that we did a few years ago. There is a break-even point, so it's not, we usually do not see the benefits linearly. So when we introduce the market penetration rate, what I have understood is that at certain level, it shows the benefits. So it goes up at 40% and goes down at 6. So between 20 and 40, for some reason, I think because we have a mix of the vehicles. So we have mix of the vehicles between regular vehicles and automated vehicles, then it creates more friction, and this friction creates more from the safety perspective. I think the study that we did with Enoch, I think back in 2018, showed that the safety benefits also has the similar pattern. There is a point that it will go down, so it will go up and go down. So we saw this in the emission analysis as well, and I said, okay, I have seen it, so we were suspicious of what is happening. I said, with the safety analysis, and almost the same pattern. This is the cumulative function, CDF, cumulative distribution function, and the point here is that this 20% NPR light blue, and then it has a hue for normal, aggressive. For 20% market penetration rate, we do not see much of the benefits, and also we did not see much of the benefits in low and medium demand scenarios. So we excluded them from the results. But we just mentioned that these are the numbers. They are not sensitive. We don't see much benefits. Also for the 20% market penetration, we did not see much benefit. For the 100% market penetration rate, it was the normal scenario was something different. So most of the observations were in the lower VSPs. Most of our observations as opposed to other scenarios. And this chart, which is my last chart, shows the sensitivity to the electrical vehicles. We introduced the electrical vehicles into the system. I think we assume that these electrical vehicles are CAVs, so we change only the CAVs to electrical vehicles. And these are the, again, normal, aggressive, and cautious scenarios. The normal with infusion of the CAVs, we saw a continuous decline in the carbon CO2, and for the aggressive, and these are the different market penetration rates. For the aggressive and cautious, as you can see, there was a point that we saw higher emission rates, and then after 40%, it continuously went down. But most of as you can see, there's not much difference between cautious and aggressive when we get to the higher market penetration rates. But normal shows benefits, and I like this chart because it's very challenging if you think about how to model CAV driver behaviors. Use just by changing the existing parameters of the Whitman 74 and 99. I think I had a discussion with Lucas yesterday that we don't have the algorithms for example, Toyota, Tesla, and we need to have some assumptions. And at the same time make sure that the model are making reasonable results. So that's so I was happy to see the chart when I saw that this everything it makes sense, even with, at high penetration rate, this is challenging to model. Again, if you want to do that, make sure that you watch the simulation. Don't just assume that it's going to be working fine. There's some ticks and trips. There are some tweaks that you need to do to your model to make everything work. And at least we had 48 scenarios, but I think we have spent some time, especially on those who had some problems. And then we fixed those. Again, George, these are all my other colleagues who worked on this. George won the best young professional paper award at the Air and Waste Management annual meeting and conference a few months ago. And so that's, I just want to highlight, we do have a TRB paper on this. We presented this at TRB last year as well. So if you're interested for the further details, I can share the TRB paper as well. And the effort is going to publication, has been accepted for the publication for the Air and Waste Management journal. They requested us to publish it. Didn't submit it. They said, okay, we want to publish your effort. So anyways, thank you for your time and any question.